If you pump water through an industrial pipe, it flows quickly and predictably. But if you pump heavy machine oil through that exact same pipe under the exact same conditions, it moves sluggishly and requires far more energy to push. The difference comes down to internal friction, a property known as viscosity. Water molecules slide past each other with ease, while the molecules in a thick liquid like ketchup or heavy oil snag and drag against one another. We measure internal drag using Newton's law of viscosity. Two parallel plates trap a fluid layer, governed by the formula tau equals mu times du over dy. This links shear stress, tau, to the fluid's dynamic viscosity, mu, and the velocity gradient, du over dy. Looking at this animated cross-section of a pipe, we can see exactly what a velocity gradient is. The layer of fluid touching the solid walls is completely stationary, but as we move toward the center, each successive layer moves faster, creating this distinct curve. We can see how this works mathematically by transitioning to a flat setup. We have two parallel plates, and the distance between them is exactly 0.02 meters. The bottom plate is moving at 0.3 meters per second, while the top plate is being pulled faster at 0.5 meters per second. The fluid trapped inside has a known dynamic viscosity, or mu, of 0.04 pascal seconds. First, we find the velocity gradient. We take the difference in speed between the two plates, 0.5 minus 0.3, and divide it by the distance of 0.02 meters. That gives us a gradient of 10 inverse seconds. Now we plug that into Newton's equation. Multiplying our dynamic viscosity of 0.04 by our gradient of 10 yields a final shear stress of 0.4 pascals. That 0.4 pascals is a precise measurement of mechanical resistance. It tells an engineer exactly how much friction force a pump has to overcome just to keep this specific layer of fluid moving. To find that initial dynamic viscosity number, engineers often use instruments like the one in this animated diagram. This is a rotational cup viscometer, which spins an inner cylinder against the fluid. The torque arrows pushing against that cylinder measure the dynamic viscosity. It represents the fluid's internal resistance to being actively forced or sheared by an external mechanism. But that is only half the picture. On this split screen, the left side shows that active mechanical pushing, while the right side shows a fluid dripping entirely on its own. That dripping action demonstrates kinematic viscosity. It measures how a fluid resists flowing when the only force acting upon it is its own weight pulling it down under gravity. We bridge these two measurements mathematically using density. Kinematic viscosity, represented by the Greek letter nu, equals the dynamic viscosity divided by the fluid's density, rho. Because density is factored in, two entirely different chemicals might require the exact same mechanical force to push through a pipeline, yet they will pour out of a bucket at completely different speeds. Let's test this logic. If a fluid has a dynamic viscosity of 0.8 pascal seconds and it experiences a shear rate of 5 inverse seconds, what is the resulting shear stress? Multiplying those two values gives a shear stress of 4 pascals. But this calculation assumes that the fluid's viscosity stays perfectly constant. Applying that assumption to the wrong chemical can ruin a piping system. This graph maps shear stress against shear rate. For Newtonian fluids like water or motor oil, the relationship is a straight line. No matter how hard you push them, their viscosity remains exactly the same. Non-Newtonian fluids behave differently. A thixotropic fluid, like ketchup or industrial paint, has a curved line. It is shear thinning, meaning the more physical force you apply, the thinner and less viscous it gets. This allows a material like paint to thin out and flow smoothly when a brush applies force to it, but instantly thicken back up to its static state to prevent dripping down the wall once the brush is removed. Getting these flow calculations right dictates the survival of heavy industrial machinery. If the calculated viscosity is too low, the fluid film breaks and metal grinds directly on metal. If it is too high, the system wastes massive amounts of electricity just trying to force the sluggish liquid through the valves. This final cheat sheet organizes the core mechanics. We have Newton's law for calculating shear stress in pascals and the kinematic equation to account for gravity and density in square meters per second. By calculating velocity gradients and mapping out how shear stress scales with different materials, engineers can precisely tune their systems to keep even the heaviest industrial fluids flowing smoothly.